So we're going to do this by pattern. It's very important that when you're learning something new, do not assume anything. Don't say, oh, it's just this because that's what I think it is. So when we're doing this, try to do everything by pattern and drawing a logical conclusion as opposed to, I think I remember this, it must be something just because I think it is. Let's go off with that, that's all. So we're going to be graphing exponential functions. So you see the variable is up as an exponent as opposed to doing y equals 2x where you just multiply. So let's just start out with something we can do, we know pretty straightforward, right? Let's do 2 to the 2 powers, right? Which equals 2 times 2, which is 4, right? And 2 to the 3 power right above it, which is 2 times 2 times 2, which equals what? That equals 8. Yeah. All right, continue all the way up. Just keep going all the way up. And by the end, you might be able to get the answer without actually multiplying out. You see a pattern growing. You just predict what the next value should be based upon just the pattern there. From 4 to 8, how do you get there? From 8 to 16, how do you get there? Yeah, so 32. It's just doubling, right? Which makes sense because our base is 2. We're multiplying by 2. Okay. So we got up to that point. Now, here's the important part about using logic and patterns to help you get our solutions. Logic and patterns only. No assumptions. So let's go the other way. So let's just count down 2 to the 1. If we follow the pattern here, what should we get? So if we go from 16 to 8, what do you have to do? All right, divide by 2. 8 divided by 4, and you get 8 divided by 2, you get 4. So what happens if you continue that pattern? What's the next number in the pattern here? 2. So therefore, 2 to the 1 equals 2. Right? So no assumptions, right? And if we keep going, what's the next number? 2 divided by 2 is? 2 divided by 2 is? 1. Yeah. So that therefore, 2 to the 0 power equals 1. Right, so see this may not be intuitive to you. That's why we want to use patterns only. A lot of people will see a 0 and say, oh no, it equals 0 because it does, and it's just because. But if you follow a pattern and look at it logically with evidence, no, clearly if we follow the pattern, it's equal to 1. Okay. So again, this may not be super intuitive right now, but that's why we're doing it. So we don't make any false assumptions from the beginning. And what if we keep on going, right? What if we keep on going? What's 1 divided by 2? Well, just 1 divided by 2, 1/2, right? So therefore, 2 to the negative 1 equals positive 1/2, which is kind of weird, because you might be thinking, well, there's a negative number, the answer should be negative, but clearly the evidence and the pattern says, no, it's not. And what if we kept on going? What's 1/2 divided by 2? Yeah, 1/4, right? And if you look closely, start looking for some more patterns and some more. Can you finish this without really doing any new calculations? All right, so take a look at this. Notice how we had 2 here and 1 over 2 right here. So to the positive 1 equals 2, to the negative 1 equals 1 over 2. To the positive 2 equals 4, to the negative 2 equals 1 over 4. So do we see a pattern here? Okay. To the positive 3, 2 to the positive 3 equals 8. 2 to the negative 3 is 1/8. So lots of patterns here that If we start from the very beginning by understanding these patterns, it makes everything a lot easier as opposed to guessing and getting used to something that's wrong and then having to rethink it all over again. Another thing to think about is that how can I write like something like 8? How do you write that as a fraction? 8 over what? 8 over 1. So to the positive 3 is 8 over 1. The negative 3 is 1 over 8. So you can look at as positive and negative exponents as reciprocals of one another. Flips the answer there. So the positive and negative is like a reciprocal. Lots of patterns. Go ahead and fill out this next one over here. See if you can do it by starting off with maybe to the second power and third power, and then fill out the rest by using patterns and relationships. So 5 to the second is 25. To the third, 5. To the fourth, 625. To the fifth, 5 to the 5. Is that 1,000? 3,000. There we go. 100. There we go. So again, if we follow that pattern down, just, divide by 5, right? 125 divided by 5 is 25. 25 divided by 5 is 5. Keep that going. So 5 to the 0 divided by 5 is 1. And to the negative 1, we have those patterns. So to the positive 1 is 5 over 1. To the negative 1 is 1 over 5. If to the positive 2 is 25, to the negative 2 is 1 over 25, right? And to this day, this is how I think of negative exponents. I always just think if I need to do negative exponent, I do the positive of it, and then I put 1 over, or I flip it, make the reciprocal. So something that's going to be different for you is seeing a negative sign and not thinking negative, but thinking with a negative exponent, it means reciprocal, not negative number. Okay? Different meaning for exponents. Okay? And we'll look at more reasons why that is. Okay? So 1 over 625, no, 125, and then 625. Right? All positive numbers. And you might have seen this before, especially like in a science class. You might have seen something like the size of an atom is 2.78 times 10 to the negative 23 centimeters. Like it's super, super tiny, microscopic small, right? Atomic size. This negative exponent never meant it's negative centimeters long. Something can't be negative centimeters. There's no such thing as negative thickness. But this negative exponent just meant it's a very, very, very small number. So you might have seen this before, maybe not thought about this negative exponent and if it's a negative number or not, but it's been around. So anything with a negative number, and you're talking about something physical, you're talking about something microscopic or atomic size, very, very small. All right, so let's look at what we've learned so far. Anything to the 0 power. Okay, what do you know about exponents to the 0 power based upon our two observations? What would you conclude from that? Yeah, anything to the 0 power, any number to the 0 power equals, what does it equal? 1. Based upon pattern and observation, no guessing, no thinking, well, it has a 0, so it must equal 0 because there's a 0 there. But, yeah, we can see clearly because why it equals 1 because of this pattern here. Now, can anybody think of an exception to this rule, by the way? having said all that, does that always work with anything to the 0 power equal 1? So what if I did 0 to the 2nd power, 0 to the 3rd power, 0 to the 4th power, and continued that? Right? So what would 0 to the 1 power be? What would 0 to the 0 power be? So 0 to the 4th would be 0 times 0 times 0. 0 to the 3rd would be 0 times 0 times 0. 0 to the 2nd would be 0 times 0. Well, what happens if you continue this pattern? What do you get? Yeah, 0 to the 1 should be 0, and 0 to the 0 should be 0, if we go by pattern. And so right here we have something contradictory. We have 0 to the 0 equals 0. And that's because this is only a number that's not positive, not negative, so it doesn't follow any normal rules. So there is conflicting answers. And if you took a calculator and you put in 0 to the 0, what would it put? Would it put the answer is 0, or would it put the answer is 1? Because anything to 0 power is 1. There's two different ways of looking at it. And mathematicians have been fighting over what's the right answer for this for a long time. Okay. So for us, we're just going to say any non-zero number. Okay. Any non-zero number to the 0 power equals 1. So everything we'll do for the next month, we'll assume every variable is not equal to 0, because none of this exponent stuff will work if the variable is actually equal to 0. Okay, so you might see that in some places where it says assume all variables are not 0. Because of this, you actually get different answers if they are 0. It's a problem. Okay, so we're going to go off and use this rule, anything to the 0 power equals 1, and assume like that anything to the 0 power, it's going to equal 1. Okay. And we'll assume variables are never going to be equal to 0, so we don't have to worry about this conflicting answer. Okay. So undefined would be the most PC way of answering that question. What is 0 to the 0 power? It's undefined. Now, what do we know about negative exponents so far? First of all, negative exponents are positive numbers. Negative exponents are positive. And they're positive, usually small numbers, small fractions. You know, microscopic or atomic, very, very, very small. Okay. But they are not negative numbers. Okay. And that other relationship we saw right here is that, well, 5 to the 2nd power is 25 over 1. 5 to the negative 2 power is 1 over 25. Right? So they are reciprocals. So negative exponent means reciprocal of the positive. Right? Again, to this day, if you ask me to do, well, what's 3 to the negative 3? The first thing I do is break it up into, okay, what's 3 to the positive 3? And then find the reciprocal of that. That's how I think about it. So if I know 3 to the positive 3 is 3 times 3 times 3, which is 27. I know 3 to the negative 3, which is going to be the reciprocal, 1 over 27, positive number. And that way, if you think reciprocal as opposed to negative, if you link that word, right, link that word reciprocal with a negative exponent, it'll keep you safe, and you won't accidentally put in negatives and things like that into your answers when they don't belong. Okay. So that's the skinny, that's the gist of all of this negative exponent, 0 exponent. And if you ever get stuck, you can always recreate this. I've seen people on tests, when I'm grading them, they have this on there because they're like, wait a minute, to the 0 power, what does that equal? And if you just draw this out, you can prove to yourself, what's the answer, as opposed to, I think it's this, and no way to check though. Okay? Remember, mathematics is always patterns. It's not guessing, it's not just random rules, there's patterns. Alright, so let's go back here and do some graphing now. Okay, let's go ahead and graph f of x equals 3x. This is just a function that we're used to graphing. We know how to do that. But let's also graph this new one, this exponential function, 3 to the x power. We know it's an exponential function because there's a variable in the exponent. Okay. So let's just do positives only because our graph is kind of positives only here. Or we could do some negative, maybe like -1. Start at -1. Go to 0, 1, 2, 3, 4. And do the same thing here. -1, 0, 1, 2, 3, and 4. And go ahead and do 3 times -1, 3 times 0, 3 times 1, 3 times 2. And then do 3 to the -1, 3 to the 0, 3 to the 1, 3 to the 2, and so on. And let's graph both of them on here. And we're only going up to 4, so let's -1, +1. Actually, let's do 3. I do every 3. -1, 1, 2, 3, +1, 1, 2, 3, 2, 1, 2, 3, 3, 1, 2, 3, 4. And go ahead and figure out what the y value should be and graph those. Okay. Go ahead and do that. You can work with someone on that. Okay, so just multiply them by 3. You know how to do that. And now we know from here, -1 power is going to be the same as 1 power, but the reciprocal. So 3 to the 1 is equal to 3. 3 to the -1 is equal to 1 over 3. 3 to the 0 power equals 1, right? 3 to the 1 power equals 3. 3 to the second power equals 9. 3 to the third power, 27, and 3 to the fourth, 81. So yeah, we have to graph all the way up to 81. If I count by tens, 10, 20, 30, 40, 50, 60, 70, 80. I count by, I can cheat just a little bit. Yeah. Count by fives. See what happens there. 10, 20, 30, 40, 50, 60, 70. I'll make a imaginary another row up here, 80. All right. So I can now graph all the way up to 81, just be a little bit above there. Put a little line up here. Okay. And graph both of them. So graph -1, -3. All right, so if I'm counting by tens, though, this is going to be -10 down here, right? The first y. So -1, -3 will be right there, really close to the axis. 0, 0. Yeah, we can do that. Let's actually do a different color. There we go. And 1, 3. So since 5 is, 5 would be right here. So 1, 3, yeah, right about there. 2, 6, just above that first line. Count by fives. 3, 9, yeah, just below, right? That's 10. 4, 12, maybe just above right there. So, yeah, there we go. There's our linear equation, y equals 3x. Right. The highest number it gets to is 12. And then let's go green. Let's go green and do this. Do the exponential. -1, 3, 1/3. -1, 1/3. Basically 0 right there. 0, 1. Okay. Right there. 1, 3. So you can see they They both go through 1, 3, so it's kind of the same at this point. But then after that, this goes to 6, but this one jumps to 9. It goes up much faster. So 2, 9, it's jumping faster there. And then 3, 27, that's way up here. See how much faster it's growing? Right? And then 4, it jumps all the way up to 81. That's way up here. This is why I had to draw a whole nother row. There's 80, so 81 is way up there. So you can see at first the linear and the exponential very close to one another, right? They even have the same numbers. They both go through 1, 3. But then really fast, since it's exponential, you see how much faster it starts going and getting bigger. Just like that. It goes up really fast. Okay, just like the warm-up there where you started off with a penny but ended up with $5 million after 30 days really fast. It gets big really fast. And if you add them all up together, not just the 30-day, yeah, it comes out to 20 million or something like that. Yeah. So just go ahead in your own words, explain what patterns that you notice. Talk about which ones grows faster, which one, which one grows as you expect, which one grows kind of in a different way. And if I just gave you the two equations, could you tell the difference if one's linear or one's exponential? How can you tell? If I gave you just the two graphs, no equations at all, no numbers, could you tell which one's exponential, which one's linear? Okay, so be thinking about that and answer those questions down below. A little hint there, the one that's linear, you know what the root word of linear is, right? It's a line. So you can kind of tell by looking at it, if it's linear, it's a line. If it's not a line, it's not linear, okay? So explain that in your own words there.